In this video, we're going to focus on the trend of atomic radius. And you can probably spot the trend already just looking at this picture over here. So take a look at the trend going down a group. So from top to bottom going down a group, what seems to happen to the size of the atom? As you might be noticing, the size of the atom seems to increase, right? We go larger, larger, and larger, and larger, and larger. And this number here kind of sort of tells you the radius of the atom. So larger atom as you go down the group. And then take a look what happens as you go across a period. So from lithium all the way to neon, for example. As you go from lithium to neon, and there's some exceptions that happen, but generally you'll see that the size tend to decrease as you go down a group. As you go across a period. So from left to right, size decreases. From left to right, size decreases. And that is generally what seems to happen within a period. So in a period, size decreases from left to right, but in a group, going top to bottom, size seems to increase. So let's take a look at that trend and let's take a look at why that is. So first of all, what is the atomic radius? It's the distance measured from the center of the nucleus to the outermost electron in picometers. And so you can see a picometer is 10 to the power of negative 12 meters. So very, very small unit of measurement. And so our first trend we identified is that within a period, so going from left to right, the atomic radius decreases. It gets smaller and smaller and smaller. And then the second trend we had found is that going from top to bottom, the atomic radius gets larger. So there's an increase in size from going top to bottom. Size meaning radius-wise. And so you can see that in the pictures over here as well. Going left to right, we have a decrease in size. Going top to bottom, we have an increase in size. And you can probably already reason why that's happening based on the two factors you learned in the previous video, the effective nuclear charge and the shielding and distance from the nucleus. So going from left to right, you have the same number of shells, so shielding doesn't really have much of an effect here. What's playing the greatest effect on the size is the effective nuclear charge due to having more protons. So there's more protons on the right side, for example, compared to the left side, which allows the electrons to be pulled in more closely to the nucleus compared to something like lithium versus fluorine. And shell number is constant, so shielding effect, not much of a factor of play there. But as you go down a group, that trend can be explained using the shielding effect. You have more shells in between the outer electron and the nucleus, and so and also the electrons are repelling the outer electrons away, and so that's why the outer electron is farther away from the nucleus, giving it a larger radius. So they're not being held as closely to the nucleus, which is why it's, again, a larger atom radius-wise. So that's how those two factors can explain the trends of atomic radius. And so we'll do some practice problems together. These two practice problems here, you can try them yourself. Pause the video, try it yourself, and then check your answers. You can also check the answers over here as well, but I'll be going over this with you to make sure you understand the concept of the atomic radius. So let me go and let's fill in some blanks here. So we identified the trends, but the atomic radius is our first trend. So a distance measured from the center of the nucleus to the outermost electron in picometers. And our first trend is that the atomic radius will decrease across a period from left to right. So we get smaller and smaller as we go from the left side of a period to the right side of the period. So decreases from left to right. So when we say that it decreases from left to right, if we were to represent it on an arrow, I erased that arrow for a reason, we would represent it this way. We'd say this is the smaller end, and it gets larger that way. So the arrow would actually grow in that direction. So it's larger here, smaller here, like that. And so the reason is because we have a larger effective nuclear charge due to more protons in the nucleus, and the shell number is constant, so shielding doesn't really have an effect. And then trend 2 was that the size or the radius increases going down a group. So down a group means top to bottom. And so if we were to draw our arrow to summarize that, we would see that the arrowhead would point down because that's where the larger one would be and the smaller one would be on top there. And so it's a great way to summarize your atomic radius trend to draw it on a periodic table like that. And the reason for that, again, is because of the shielding effect. There's a greater number of shells or energy level in between the nucleus and the valence electrons. So let's go ahead and try some practice problems out, and I'm going to show you how to use the periodic table to do questions like this over here. We'll actually start off with question number 2. It's a little bit easier because we're only comparing 2 atoms at a time. So we're going to compare aluminum and boron, and we need to circle the atom that has the largest atomic radius in the pair. So between aluminum and boron. So let's go to our periodic table. Here's aluminum, and here's boron. They're not within the same period, so we're looking at a trend going down a group. As you know, as you go down a group, the radius should get larger because you have more shells. So aluminum will be the larger atom in this case over here. And just to confirm, yep, it seems like aluminum is larger. You won't be given this periodic table on an assessment. You'll have to use the real periodic table. So you need to be able to use that, but we'll use this to confirm our answers. So between sodium and aluminum. So here we have sodium, and here we have aluminum. Now we said these are within a period. So within a period, the size decreases as you go from left to right because you have more protons. So aluminum will be smaller. That means sodium is going to be larger. So sodium should be the larger atom. And let's take a look if that's the case. Yes, it looks like sodium is larger than aluminum in that picture. Next, between sulfur and oxygen. So let's take a look at sulfur and oxygen. So here's oxygen, here's sulfur. They're going down a group. Going down a group, the one below should be larger due to more shells, so sulfur is the larger one. So there we go. Sulfur is the larger one, and it looks like it makes sense. Sulfur does look a little bit larger. Between oxygen and fluorine, let's go take a look there. So here we have them within the same period. So going from left to right, we get smaller towards the right side. So fluorine is the smaller one, making oxygen the larger one. There are exceptions, but I won't really focus on the exceptions now. We're just going to focus on using the trends in general. So oxygen is larger than fluorine, so it is a little bit larger there. And then bromine and chlorine. Let's take a look at that. So between bromine and chlorine, that's within a group. So we get larger as we go down because you have more shells. So bromine should be the larger element in terms of radius, and it does look like that's the case here as well. And then lastly, magnesium and calcium. So let's see. Here we have magnesium. Here we have calcium. We're going down a group. So more shells for calcium, so calcium's larger. So you should be able to compare atoms like that and reason sizes like that as well using the trends. And even though there might be exceptions, I just expect you to use the trends right now, unless I tell you otherwise. But for now, focus on the trends. So even if something is an exception, I'm really going to just kind of ask you to look at the trends rather than focus on the exceptions. So let's rank the following elements by increasing atomic radius. And students have a lot of trouble with that word usually. So increasing means from smallest to biggest. That's what that means. So find the smallest one, write it first, and then write the biggest one after. And when you have a series like this, it's nice to compare the easier ones first. So we have carbon, aluminum, oxygen, and potassium. And we need to figure out how to write this out. So let's go look at a couple elements here. Between carbon and oxygen, oxygen would be smaller because it's more to the right. So oxygen we know is smaller than carbon, so we know that. So I'm going to start sort of ranking some of the elements here. So oxygen, carbon, and I did those two. Okay, great. Let's go try to compare more. Let's go see if we can compare maybe aluminum to some of those. So here we have aluminum. And so you need to realize that carbon and oxygen are on top of aluminum, and they're also to the right of aluminum. So even if aluminum was in the same period, aluminum would be larger because it's more towards the left side. But aluminum now is towards the left and also towards the bottom. So aluminum is larger than both oxygen and carbon. It's larger than both of them because it's lower and it's towards the left. So that makes our lives a little bit easier here. So I'm going to put aluminum over here. And I'm not sure if my order is really good yet because it's left to compare my potassium. So I'm going to go take a look at potassium and see where it might fall compared to the oxygen, carbon, and aluminum. So if we look over here, we have potassium. potassium is to the left as well and towards the bottom. So if potassium was in the same row as aluminum, potassium would be larger anyways than aluminum. But it's kind of a double whammy larger because it's also down. It's also in the next period. So there's more shells there. So potassium is larger than even aluminum. So this seems like it'd be the correct order. We put potassium over here since it's the larger one. And usually I write it like this. I put oxygen is smaller than carbon. Carbon is smaller than aluminum. Aluminum is smaller than potassium. So radius of oxygen is less than radius of carbon, which is less than radius of aluminum, which is less than radius of potassium. And so generally, you want to compare just a few at a time, make some space, try to find the order and place those elements in there. There might be a little bit of a trial and error sort of thing happening there, but if you get good with identifying radii, that's the plural radii, in pairs, then you'll be able to do questions like this as well, and you'll see some more of those styles of questions in your worksheets. So in the next video, we're going to take a look at the next trend, which is related to atomic radius, but it's now the ionic radius.